Okay, so over the course of the last few videos, we've been looking at the case where lambda 1 is not equal to lambda 2. However, in these videos we're going to start to look at where lambda 1 is equal to lambda 2 and we have a repeated root. So let's take a look at a quick example. Okay, so the method is going to be exactly the same as video 05.2 in the calculus playlist. So first off we need to find the fundamental solution. And we can do that by using the lambda substitution method. So here we have lambda squared, because we know that the lambda function is the same as taking the first derivative with respect to t in this case. So if we take it twice, this would be lambda times lambda, so lambda squared. Minus 4 times the first derivative, plus 4 times the 0th derivative, is equal to, and to start off with we're just finding the fundamental solution. So we make the right hand side of this equation 0. So we can either use our quadratic formula here, or we can just use factorization. And this is quite a simple example, so we can see straight away that this factorizes to lambda minus 2 times lambda minus 2. So therefore lambda is equal to positive 2. And when you have a repeated root, the general formula for the solution of the lambda equation, this here, is going to be equal to, we'll call it our fundamental solution. It's equal to some constant c1 times e to the lambda t plus another constant c2 times t e to the lambda t. So already we've found that our fundamental solution, therefore, in our specific case here, is equal to some constant c1 times e to the 2t plus some other constant c2 times t e to the 2t. And there we have our fundamental solution. If you're looking for some more information about the fundamental solution, we went into a lot more detail in the calculus playlist video 05.2, so I would suggest you check that out. I'll leave a link in the description. Okay, so now that we have our fundamental solution, it's time to find our particular solution, which is specific to the right hand side of this equation. And since the right hand side of this equation is equal to the superposition of two properties, our particular solution also needs to be a superposition of each individual result. So if we focus firstly on the 2 sine of t here, and we'll call this number 1, our particular solution, we'll call this particular solution 1 of t. And since we have a sine function here and we need to take the second derivative, we know that the derivative of sine is cosine, so we need to include all of the possibilities of the sine and the cosine in our general answer. So our particular answer for this will be a times the sine of t, but we can't forget about the cosine aspect as well. So now we need to know the first and second derivative of our first particular solution. So sine differentiates to cosine, so this will be a times the cosine of t, and cosine differentiates to minus sine, so this would be minus b times the sine of t. And if we take the next derivative, p1 t, again cosine differentiates to minus sine, and sine differentiates to cosine. Now all we need to do is replace our general equation here with our particular one here. So everywhere we have a second derivative, we need to replace it with our particular solution of the second derivative. So we have 1 times the second derivative of t, so we need 1 times the second derivative of our particular solution of t. So we have minus a sine t minus b cosine of t. Then we have minus 4 times the first derivative, so a cosine t minus b sine of t, plus 4 times the 0th derivative. Use green 4, so that's a sine of t plus b cosine of t. This one here. And is still equal to 2 times the sine of t. Okay, so now if we just focus on the sine terms here, we find that 3a plus 4b is equal to 2, and then if we focus on the cosine terms, we find that 3b minus 4a is equal to 0, and then if you solve these simultaneous equations, you get that a is equal to 6 over 25 and b is equal to 8 over 25. So that means that our particular solution 1 of t is equal to 6 over 25 times the sine of t plus 8 over 25 times the cosine of t. Okay, so for our second particular solution, we need to account for all possibilities of any constant times e to the 2t. So our general solution for this is just going to be some constant, e to the minus 2t. So therefore our first derivative is just going to be minus 2a e to the minus 2t, and our second derivative of our second particular solution is going to be 4 times a e to the minus 2t. And then we can use the same method here, so everywhere we have a second derivative, we just replace it with the second derivative of our particular solution. So we have 1 times the second derivative, so we have 1 times this, which is 4 e to the minus 2t. Then we have minus 4 times the first derivative, plus 4 times the 0th derivative, is equal to our 6e to the minus 2t. So this is 16a is equal to 6, So therefore A must be equal to 3/8. So therefore our second particular solution is very simply 3/8 e to the minus 2t. And like I said earlier, I go into a lot more detail in video calculus 05.3. So if you're getting lost at any point in this, just go back and have a look at that video. And again, I'll leave the link in the description. So now that we have our fundamental solution and our particular solution, all we need to do is find our general solution by adding them both together. Okay, so now that we have our general equation, we're almost there. The only thing left to do is to work out what C1 and C2 are, because we still have two unknown constants in our equation. And the way we do that, you might know from the last video, is that we need to solve an initial value problem. Okay, so to solve an initial value problem, we first need two initial values, because we have two unknown constants. So if we say that our system x at time equals 0 is equal to position 0, and that the system's velocity at time equals 0 is also equal to 0, we should be able to solve this now. And when I say velocity, I just mean the first derivative of position, which is its physical description. So now all we need to do finally is to go through this equation and input t equals 0 and compute it equal to 0. So at time 0, we have C1 times e to the 0, so we just have C1. Next we have C2 times t, so this term will go to 0. And we know that the sine of 0 is also 0, so this term will also go. And we know that the cosine of 0 is 1, so this will retain. So we have plus 8/25. And this will be e to the 0 again, so this will be 1 times by 3/8. So we'll keep the plus 3/8. And still is equal to our initial condition, which was 0. So then straight away from this equation, we can derive that C1 is equal to minus 139 over 200. Okay, next we can use the first derivative and input t equals 0 into that. So we have the first derivative at t equals 0 is equal to, and we have c1 times e to the 0. If we take the derivative of that, that's going to be 2 times c1 e to the 0. So we would have 2 times our already calculated c1 value. And then if we take the derivative of this, we need to be careful because we need to use the product rule. So this would be C2 times e to the 0, which is just 1, plus 2 times C2 t e to the 2t. And since it's times by t and we're inputting t equals 0, this will go away as well. And the next term, when we differentiate sine, we get cosine. So the cosine of 0 is 1, so this term is going to stay here. So we're going to have plus 6/25. And when we differentiate cosine, we get minus sine, so that will go to 0. And then when we differentiate this, we'll have minus 2 times 3/8 e to the 0. So that stays there. And as before, still equals 0, because that's the initial condition that we set. So from this, since we already know C1, we can get that C2 is equal to 19/10. And then after all this work, this horrific looking thing at the bottom is our final solution. And I know a lot happens in this video, but if you break it down into these 4 simple steps, you'll be able to handle second order ODEs just fine. So the first thing we did is we found our fundamental solution, and if you're looking for a better example on that, you might want to check out Calculus playlist video 05.2. And then we found our particular solution, which again, if you're looking for a better example, or a longer, more explained example should I say, if you look for Calculus playlist video 05.3, I explain it in a lot more detail there. And then we found the general solution by adding together our fundamental solution and our particular solution or solutions. And then we used a set of initial conditions to calculate what the final unknown constants were. And again, I explain that in a lot more detail in Calculus video 05.4. I will leave the links for those 3 videos in the description. Thank you very much for watching, and in the next video we're going to look at the case where lambda has both a real and an imaginary part. I really hope this video helped you, and I will see you in the next video.